Good morning to everyone. I am G.BALAMBIGAI, Assistant Professor of EEE. I am going to take the subject of electrical drives and actuator for second mechatronics who are in third semester. So we are going to see about the SCR, silicon controlled rectifier. SCR belongs to thyristor family. Some of the devices of the thyristor family are here. That is, first one is silicon controlled rectifier, gate turn off thyristors, reverse conducting thyristor, static induction thyristor, gate assisted turn off thyristor, light activated silicon controlled rectifier, mass controlled thyristor, triac. Out of all these devices, SCR is the most commonly used thyristors. So here SCR characteristics and modes of operations we are going to see. So first SCR. So the SCR we are having three terminals. That is, first one is anode, cathode and gate terminals. So how it is going to operate? So it is a 4-layer device, that is PN. So if you are going to, already we have seen about what is biasing. Biasing is giving a supply toward the devices, the device starts to burst. That the biasing, we can say that of forward bias and reverse bias condition. So if a positive is connected to a positive and negative is connected to a negative, we can call it as a forward bias condition. And if a positive is connected to negative and a negative is connected to a positive, we can say that it is in reverse bias condition. So here there are three different modes of operations for an SCR to work on. First one is reverse blocking mode, and second state is forward blocking mode, and third one is forward conduction mode. So here first we are seeing about reverse bias SCR. So in reverse bias SCR, as we have said that if your positive is connected to a negative and if your negative is connected to a positive, we say that it is a reverse bias. So SCR in forward bias condition, here say that P is positive, that is anode terminal is positive, it is connected to positive, and your negative terminal, that is cathode, it is connected in negative. So we can say that it is in forward bias condition. And forward conduction mode, when SCR is forward bias, then it goes into the forward conduction by the following techniques. When that we can say that when anode to cathode voltage is higher than that of your breakover voltage, whenever the device is going to turn on, so it will, after it attaining the breakover voltage, it will start to turn on. And then when it is going to be turned on, it can be turned on by either we are giving by increasing the forward voltage or by giving a gate pulses. When dV by dt exceeds the permissible value, also it goes for the forward conduction mode. When gate cathode junction is exposed to light, also we can go for the forward conduction mode. So this is the static VA characteristics of the SCR. That is VA characteristics, we can see that the in x-axis you are anode voltage, anode to cathode voltage. Always we say that the voltage in as across the circuit, that is here we can take the voltage across anode and cathode. Generally we will mention a current as one terminal around IA, also we can mention it, but when we refer voltage value, we have to say the two terminals because no voltage is connected across your terminals. So VAK and IAK. So same thing here, if you take in the minus VAK, and same that here minus IAK. So your SCR will conduct in your forward conduction mode, So we can say that is a forward blocking state and forward leakage current after it attains a breakover voltage, that it has mentioned as VBO, forward breakover voltage. After attaining that, it starts to conduct. So that is forward conduction on state. When your given gate current has been increased, that breakover voltage will be a little bit earlier. So that is, we can say that IG1, IG3 is greater than IG2 is greater than that of your IG1. So when it is given in the reverse bias condition, if we go for the reverse blocking and after it's a reverse breakdown voltage occurs, it will starts to stop. That we can call it as here in the reverse blocking period, after it attaining the reverse breakdown voltage, it will not work. It will starts to the voltage value will start to be in the same that saturation level. Next we are going to see about that latching current. What is meant by latching current? We are saying that when your SCR is going to turn on by giving an gate pulses, that is only by increasing your anode current value it is going to be turned on. When it will get turned on, that is after it attaining the latching current, it will start to turn on. At the same time, when it have to be turned off, it have to be bring back to a current value that we can call it as a holding current. So here latching current means it is a minimum forward current that flows through the SCR to keep it in the forward conduction mode, that is in on state at the time of triggering. Triggering is nothing but a turning on. If the forward current is less than that of the latching current, SCR does not turn. After it attaining the latching current, that is here IL, it will start to turn on. So when we increase the gate current value, if you are attaining your latching current, then it will start to turn on. At the same time, when you have to turn off your SCR, you have to bring back your anode current to the holding current value, then it can be turned off. So here this is called holding current, the minimum value of anode current for which the SCR goes from a transition from forward conduction to forward blocking mode, that is it can be turned off. So once we have to turn off your SCR, we have to bring back your anode voltage below a holding current value. After it attaining a holding current value, it will be turned off. So the SCR, you can say that of a 2 transistor models, the operation of SCR can be helped with the help of 2 transistor model. So when your 2 transistors are connected like this, we can say that it is worked as a SCR. So PNP transistor and your NPN transistors are connected, then it can work as an SCR. So what is the switching characteristics and why we have to go for a switching characteristics? So we are going to use these devices as a switch for the converted operations, that is for power conversion operations. So we are going to use these devices as a switch alone. So before going to see a device as a switch, we have to know that when your switch is in on condition, what will be the value of the voltage across your switch and what will be your current value. So normally we can say that in short circuit condition, we can say that the voltage across it will be 0 and the current will be what will be the applied current. At the same time, if your circuit is in open condition, the current value will be 0 and your voltage value will be what we have applied in the voltage as an input voltage. So same we have to consider here. Your SCR is going to act as a switch here. So if it is going to act as a switch, if you take the voltages across your switch, the voltage value is going to reduce and your current value is going to increase here. That we can see here. So we are going to give a gate pulse here. So gate, that is, it is SCR, we can say that SCR is a current control device. So by controlling your current only, this device is going to be operate as a switch. So we are going to give a gate pulse, that is gate current value. As a gate current is going to increase, your anode value is going to, anode current value is going to increase and your anode voltage value is going to decrease. Once your device is going to use as a switch, that is if it is in the on condition, it acts like a short circuit. Then only we will get the output across your load. So whatever we are giving a supply in the supply, that if your device is acting as a switch, if you take the voltage across your device, the voltage value will be 0 since act as a short circuit. That is, we are going to close the switch. So then we can say that it is in the on condition. So your current value is going to increase and your voltage value is going to decrease. So this is the switching characteristics of your SCR. So here we are giving a gate current. So if as a gate current is going to increase, your anode current is going to increase and your anode voltage is going to decrease. So we can say that a turn on condition. So here T on split into 3 time periods, that is TD plus TR plus TP. So what is meant by TD? It is a delay time period. So first it is going to increase slowly from the value. So first it will be in the forward leakage current. That will be a very minimum of below 0.1. So it will be in 0.08, 0.07, 0.06 in the top. So when it is going to reach your 0.1 IA, we can call that time period as a delay time period. So the next one is TR, rise time period. That is where anode current is going to increase from 0.1 IA to 0.9 IA. At that time we can call it as a rise time period. From 0.9 IA to IA, we can call that time period as a peak time period. So turning on of SCR, that is turn on time of your SCR, can be split into 3 different time periods. First one is delay time period, rise time period and peak time period. After it is attaining the peak value, it is to be in the on condition. So we will be in the saturation, that is IA, the load current is. Once we are going to turn off, it is going to decrease. The current is going to decrease and your voltage value is going to increase. So if you want turn off, means that is your current value of your anode current value is going to decrease. So here we have mentioned the word commutation. So commutation, generally in SCR it cannot be turned off by removing the gate signal. So we are need for a circuit to reduce the gate current value, that is below the holding current, to turn off your SCR. So the turning off of the SCR, we can call it as a commutation. So we have mentioned here as a commutation. So turn off time period we have mentioned as a two different time period, that is TRR plus TGR. TRR means it is a reverse recovery time period and TGR means gate recombination. So overall turn off time of your SCR, we can mention it as a TQ. Here we have mentioned as TC also. TC means it is a circuit turn off time. As we have seen here, the circuit turn off time should always be greater than that of your device turn off time. Device turn off time is nothing but here TQ, that is TQ means a thyristor turn off time. So the overall circuit turn off time period will always be greater than that of your device turn off. First the device has to be turned off, then only your circuit has to be, the entire circuit has to be turned off. It is a safer operation. So we can say here that TQ is split into TRR plus TGR. So T1, T2, T3. Here it's a recovery time period and here we can call it as a recombinations. So this is a PA characteristics of your SCR. So next we are going to see about the gate turn off thyristor. This is a one type of your SCR. So what is the difference between your SCR and your gate turn off thyristors? So as we have mentioned here, gate turn off. SCR, in SCR we are going to turn on by giving a gate signal, but it cannot be turned off by removing the gate signal. So to turning off the thyristors, that is SCR, we have to go for a circuit to turn off your SCR. So it is not a easy one. But in gate turn off thyristors, it can be, if the gate pulse is given, it can be turned on, and if you remove the gate pulse, it can be turned off. That is the main difference between your GTO and your SCR. Here we can say that it is very similar to that of your SCR. Here anode, cathode and gate. But in gate, here we have given two arrow. That is, it can be turned on by using a gate signal and it can be turned off by removing the gate signal. That is the difference between your GTO and your SCR. So here observe that the structure of GTO is similar to SCR. Gate and cathodes are highly interdigited with various geometric forms. This maximizes the periphery of the cathode and minimizes the gate cathode distance. There are N plus regions at regular intervals in P plus anode layer. This N plus layer makes a direct contact with N minus. So this is called anode short. This speed ups the turn off mechanism of GTO, that is not in SCR. The operation of GTO can be explained with the help of two transistor analogy, that is the gain of PNP transistor is reduced. This reduces the regenerative action. Hence turn off thyristor GTO can be achieved by negative current from the gate. So this is a VI characteristics of the GTO. This is similar to that of your SCR. So we can say that this is the because of your anode short structure. So advantages, limitations and applications of GTO. Advantages, we can say that higher voltage blocking capability. So gate has full control over the operation of GTO, that is not in SCR. That is only for turning on your SCR. If you give a gate pulse, it turned on. But by removing the gate pulses, it cannot be turned off, but GTO can be turned off. So we can say that gate has full control over the operation of GTO. And low on-state loss. So high ratio of peak surge current to average current and high on-state gain. So there will be some limitation. Here GTO requires large negative. Even if you give a gate pulse, negative gate pulse, it will be turned off, but it requires large negative gate current to turn off the device. Hence they are suitable for only low power applications and very small reverse voltage blocking capability. So it will be easily affected and it will be shorted. Then switching frequency is very small, so it cannot be used for higher power application. So applications, it is mainly used for only low power applications. Since the switching frequency is very small, it cannot be applied for the high power application. So it is used for induction heating and motor drives. So next we are going to see about power MOSFET. As we have seen that SCR silicon control rectifier, it is a current control device, but MOSFET, what is an expansion of MOSFET? Metal oxide semiconductor field effect transistor. So it is a voltage control device. So by controlling the input voltage, that is VGS, we can able to control these devices. So it is a voltage control device, but SCR is a current control device. So in the MOSFET there are two types, N channel and P channel, and according to the structure we can say that it is a depletion type MOSFET and enhancement type MOSFET. In both depletion and enhancement, that there are N channel and P channel MOSFETs. So this is a symbol of your N channel MOSFET and this is a symbol of your P channel MOSFET. What is the difference we have observed here? That is an arrow. So in N channel, so here this arrow is the main difference between your N channel and P channel. This represents the flow of current, that is will be always from positive to negative. So here it is an N channel, here it is going inside, that is from positive to negative. So this is the positive terminal, so positive to negative it is entering. This is the positive one and this is a negative one. So here it is entering from positive to negative. This is the main difference between your N channel and P channel. As we have already discussed this thing in the BJT also. In BJT also we have three terminals that we can say what is the base, collector and emitter. What will be the main difference between your collector and emitter? That arrow. So that will be for NPN transistor, if it comes from positive to negative. For PNP transistor, it goes from positive to negative, so it will goes inside. So the same thing will be for the MOSFET also. So this is the structure of the MOSFET. This is the structure of N-channel enhancement MOSFET and formation of inversion layer. So here pinch off voltage, what is meant by pinch off voltage? When the gate source voltage is reduced and if it is made negative, the depletion layer is created as the gate source is further reverse biased, the complete channel is depleted and no current flows from drain to source. The gate source voltage at which this happens is called as the pinch off voltage of MOSFET. So this is the steady state or VA characteristics of MOSFET. As we have already mentioned here, this MOSFET is a voltage control device. When we compare with a BJT is also a current control device. The same VA characteristic we can obtain there also, but here we will mention that as a IB value. So for different values of IB, we can get the VA characteristics. So here we have seen that for different voltage value, that is input voltage. So VGS value, we can obtain this VA characteristics of your MOSFETs. So we can say that MOSFET works under 3 different regions. So first one is cutoff region, an active region and ohmic region. So by controlling the voltages value, we can able to control the working of your MOSFETs. So when we are going to use this MOSFET as a switch, this is a switching model of MOSFET. So here inbuilt of capacitor will be there. This capacitor is going to help for the switching function. That is, the switching characteristics mainly varies with the input capacitance CISS and the output impedance of your driver circuit. So gate current flows from gate to source instantaneously to charge the input capacitance. Therefore, the lower the output impedance of the driver circuit, the faster will be the switching speed. So in addition, switching characteristics of power MOSFET has the advantage of switching larger current of faster than your BJT. Why? Because in power MOSFET does not have minority carriers, but BJT it works under minority carriers. So there are 10 to 100 times faster than the comparable BJTs. So during cutoff, the gate to source voltage is less than that of a threshold voltage. To turn on, the VGS has to be increased well above the threshold voltage. As we have mentioned there in your SCR, after attaining the latching current, it is going to turn on. Similarly, in MOSFET, during our cutoff of the gate to source voltage, if it is less than the threshold voltage, so to turn on your MOSFET, VGS has to be increased well above a threshold value. So the drain to source voltage must be less than that of your VGS to VGST. So the switching characteristics of power MOSFETs are influenced to a large extent by the internal capacitance of the devices of the gate driver circuit. So this is your switching model of your MOSFET and this is your switching characteristics. As we have seen in your SCR, the turn on of SCR is split into 3 different time period, that is T delay, TR and TF, but here it is TD on and TR, that is delay time period, that is from 0 to VGST. If it is we call it as a TD, delay time period, and from VGST to VGS peak value, we can call it as a TR, rise time period. Then after attaining that, it will be in the conduction state. Once if you are going to turn off, so it is going to be reduced. So from the peak value, from V1 to a peak value, we can say that time period, we can call it as TD off, delay time period. But we have mentioned that here during turn off, so it is TD off. During turn on, we have said that TD on condition. And then next to TF. TF means it is a fall time period. So it is going to be reduced to 0. So that time period we can call it as a TF. So we can say that the turn on delay, that is TD on, is the time that is required to charge the input capacitance to threshold voltage level. The rise time is, it is a gate charging time from threshold level to the full gate voltage VGSP. So during rise time, drain current rises from 0 to full on current ID value. Thus the total turn on time for MOSFET, we can say that TD on plus TR. So the turn on time can be reduced by using low impedance gate rise source. As the MOSFET is the majority carrier, turn off process is initiated soon after the removal of gate voltage. So turn on time period, so TD off can be mentioned as the TD off plus TF, that is fall time. The fall time is, it is the time that is required for the input capacitance to discharge from the pinch off region to threshold voltage. So if VGS value is less than that of your VGST, the transistor turn off. So during fall time, the drain current reduces from ID value to 0. So this is the switching characteristics of your MOSFETs.